So good afternoon, everyone. I'm Zihua from University of Munich, and today I would like to present a topic about modeling co-seismic wave speed changes of rocks and soils from source, path to site. Maybe I start from defining my range of study. Here I cannot move, no. Okay, here I show an example of from our group. It is not by me, but by a previous PhD student, Taufik. They modeled the Amatrice earthquake in 2016 in Italy. So there are three major components in this model. The first one is this gray rectangles that represent the fault where the earthquake starts, and these are the source of the earthquakes. And the second component is this 3D velocity structures that are composed of the tetrahedral elements, and it's representing the path where the wave are propagating until it reaches the ground. And the third component is topography and also some sedimentary basins that constitute the side effect, which typically take place in the depth of a few hundred kilometers. And there are nonlinearities in all these three components and to different degrees. The first nonlinearity is at the source, where due to the strong dynamic strain and stress, the rocks are damaged, and I here show an example of the experiment on a rock sample in the lab. The x-axis is the loading time, the y is the stress on the rock sample. We see that when it reaches above 200 megapascal, there is a sudden drop of stress, and that corresponds to the failure of the rock. And this also happened near the earthquake sources. That contributes to the awful damage of the fault. And the second type of nonlinearities is what we in this workshop are very much focused on. I call it the path nonlinearities. It's the when we use the cross-correlation based method, how we derive the dV over V, and these also observations in the lab where they just cyclically loaded the rock samples and at the same time monitoring the velocities changes. And here in this example I show here, the velocity change is very small, less than 1%, and this is typical what we expect for this path effect. And the nonlinearities can become even stronger in the sites because of the shallow sedimentary basin or sedimentary materials. They have very low velocities, and there they amplify the strain field and therefore introduce stronger nonlinearities. And here is the stress strain curves where we have this loop, which is called the hysteresis, and that's when where the energies are dissipated during the propagation of the waves. And I'm trying to develop a code that can simulate these nonlinearities. And I I start from the models that I use one by one. I start from the source. This is our current understanding of how the fault zone looks like. It typically consists of a thin layer of fault gouges that represents the weakest part of the fault, and we usually simplified it as the fault plane. And we have a frictional force on the fault plane and the two sides on the fault plane that slip against each other. But at the same time, there is a damage zone or that are diffused from the very thin layer of fault gouges. And this contributes also to some source effects. And in 2014, the Kovsky proposed models that based on continuum mechanics that can describe how the stress increases with the strain, and also at some point it fails, the stress level suddenly drops. And it is important to study source effect for many reasons. I list here two of them. The first one is the source frequency, because when we have this sudden drop of velocity, it contributes to the high frequency components of the source radiated from the earthquakes. And the second one is the fault interactions. Because we have this diffused damage zone, it changes the moduli next to the fault, and it will perturb the stress field that are adjacent to this nucleated fault. And therefore, it's important to account for nonlinearities near the source. And also we have the path nonlinearities, and these I think many of us are familiar with. I just saw an example in the field in Japan. It is conducted by Brengel et al. In 2014. And this is color-coded with velocity changes after the Tohoku earthquakes. The more reddish the color, the stronger the velocity changes is. And there are also similar observations in the lab, where they again put the rock samples and they load it cyclically. And at the same time, they monitor the wave speed of the rock samples using acoustic sensors. The key feature I want to draw attention here is in this dashed red rectangles, it's at the end of the perturbations there is an instantaneously unrecovered damage. And this is very much similar or comparable to what we observe in the field. After the earthquakes, we have unrecovered damage. At least it only recovers at a longer time scale. So these are the path nonlinearities that we're interested in. And second is the source, is a side effect. I think not many of us are familiar with this side effect maybe, so I just briefly introduce where it might be the most prominent. It's inside the sedimentary basin. A schematic plot of the sedimentary basin is like this. Inside this red rectangles, there is this where the softer materials are less consolidated and usually represented with a low shear modulus and low wave speed, therefore. And this low wave speed will amplify the strain field and leads to, in the earthquake engineering community, they describe this nonlinearity with the shear modulus curve. And this plot describes how the relative shear moduli drops with the amplitude of the strain fields. I mean, the larger the strain field we apply to soils, the more damage that we introduce. And it's just comparable of the model that we use in our simulation to our previous models that describe the soils. Just a brief idea of what the amplitude can reach in the sedimentary basins. It typically can reach 5,000 microstrains, and it corresponds to a shear modulus reduction of around around 60%. So this is the nonlinearities that we can expect in the site. And there's additional effect that I said, which is the hysteresis curve. I again show an experiment from the lab. This is conducted on the soil sample, and on the y-axis is the strain field, so it's a cyclically loading the strain with a certain amplitude, and at the same time, it measures the stress and it plots the stress strain curve, and that's what I show in the very beginning. It starts from this loop, and it slowly the slope becoming lower and lower, and this represents how the modulus of the soil are dropping with the cyclic loading. And this is what the model that we use to simulate this effect. And it is color-coded by the number of cycles we applied. So you see, when we increase the number of cycles, the modulus are dropping. So these are the models that we use for accounting for these nonlinearities at different places. And I give a summary now. We have accounted for the moduli changes on a dynamic loading. We account for this moduli reduction curve for soft sediments, and also this rock failure on the high level of loading, and also this energy dissipation that we observe in the soils. And all these are can be generally written into a form mathematically defined as nonlinear hyperbolic equations with a source term. And to solve this mathematical system of equations, we choose the Adler-DG algorithms, which is a combination of the finite element and finite volume. So, but they take the merits of both methods so that it can account for the nonlinear effects in the wave simulations. So these are the method I use. I will not talk about the detail of the algorithms, but I'm happy to discuss with you if you're interested in after my talk. I would like to share with some results that we got from our simulations. So we tried to model the nonlinear effects in 3D, and we choose the site in Kathmandu Basin. We used the finite fault model, which means we define the slip rate distribution on the faults that are in space and time, and to describe how the earthquake sources look like. And then we build up this 3D velocity structures. It is a layered structure, and also with the sedimentary basin and inside these rectangles. We also include the topography in Kathmandu Valley. And at the same time, in this basin, we vary the sedimentary basin depth, which means the thickness of the soft materials that we have. And again, we implement these nonlinear models that we constrained from other models. And then all these are implemented in the software SISO, which is maintained in our group, and it is built for earthquake simulations, and now we extended it to simulate nonlinear wave equations. So as we maybe all know, the frequency that we can resolve depends on mesh sizes and the wavelength of the wave field. So it means when we are in the low velocity regions, then we need to refine the mesh more because the wavelength here is shorter. So we build such a mesh so that we can resolve frequencies up to 0.5 hertz. And these are 2 million tetrahedron element mesh. And we the SISL is a highly parallelized code, so we can run it on supercomputers. For this simulation, it runs on 256 nodes, which is around 10,000 cores. And because of the performance engineering work from our collaborators, it is able to run this simulation within 3 hours. So this is the setup of our model. And let's go to some of the results. I start from the path nonlinearities, where most of us in this workshop are interested in. So this is a plot that I put at the depth of 12 kilometers. And the dashed black curve is the intersection of the fault plane with the depth slice at 12 kilometers. And we can see that the closer we are to the fault, the larger the wave speed changes are. And at the same time, there is a spatial pattern that we want to know what is correlated with. So let's take a look at the fault slip distribution on the fault plane, and we can see it's actually very much correlated to the fault slip that we have on the Earth for the earthquakes. So the stronger the fault slip, also the stronger the wave speed changes. And to take a closer look into the amplitude of the wave field, I draw a circle with a radius of 70 kilometers. And in this, within this range, we can see the wave speed changes are larger than 0.01%, and this is the value that are measurable with the coarse correlation-based method. And this is at a depth of 12 kilometers. And if we look into the depth that are at 2 kilometers, the distribution pattern is not much changed. And also, we can still expect velocity changes that are larger than 0.01% within a range of 70 kilometers. So these are the path effect. And if we look into the site where the sedimentary basin are, we will be able to see that the wave speed changes are much larger. We can see the peak wave speed changes are 64%. So this means the nonlinear effects are much stronger in the site, and it also has this heterogeneous distribution pattern. This is actually also correlated to the sedimentary basin depth. You can see the places with a deeper or thicker layer corresponds to the place with a higher velocity drops, or wave speed drops. And these are about the wave speed drops, and it just shows the strong nonlinear effect in the sedimentary basin, and it also has effects on the ground motions. We compare different models, the elastic model, the viscoelastic model hiding behind the bars, and the elastoplastic and our nonlinear models. So we pick one station marked with these red rectangles, and here is the waveforms. So for the elastic case is plotted with the blue curve, the viscoelastic case is with the orange curve, and the plastic case with the green curve, and then this our nonlinear damage model with this red thick curve to highlight its importance. There are two basic features in this nonlinear damage model that we implemented. It has an effect on attenuation of the wave, and this is directly connected to the wave speed changes. And the second thing is if we plot the spectrogram of the seismogram, we can see that there, with the nonlinear model, there is a frequency shift to our lower values. It means it's the nonlinear model that shifts the frequency components of the seismograms to lower values. And this is also observed in earthquake engineering observations. So these are the two effects that we found most prominent. And so far I talked about the path nonlinearities and site nonlinearities, and I would also like to take this chance to share a teaser about how the source nonlinearities have an effect on the earthquake processes. So I use this step-over setup, which consists of two vertical fault planes that are strike-slip faults, and they are separated by 3 kilometers away from each other, and they nucleate. I nucleate the earthquake from one of the faults, and to see how the second fault reacts to the nucleation of the first fault. To describe the slip behavior on the fault, we use the slip weakening law. It just says the shear, the friction coefficient drops with the slip distance. It's the simplest weakening law that we can use for fault modeling. And let's start from this elastic case. You can see the nucleation starts on one of the faults, and it ruptures in the entire fault. But in the elastic case, the second fault is not activated. So this earthquake will just stop. But when we have this nonlinear alpha damage, again, the first fault will be nucleated, and then it's ruptured the entire fault. And after the rupturing process, we take a look at the bottom fault here. This is the second fault plane. And we can see the damage starts to accumulate on the second fault. And after a while, this damage will lead to the creeping of the fault of the second fault. And the creeping front is going to move slowly forward. And at some point, it's going to nucleate the second fault, which means it will lead to an eventual rupture of the entire second fault. And it's happening now. Yes. And maybe we can take a closer look onto the cross-section of the fault. We cut through the fault plane and see what's the damage look like. So these two black lines are the faults. And we see how the alpha damage really develops. This starts at the end of the first ruptures, and this localized damage zone will extend from the first fault to the second fault, and that leads to the stress changes on the second fault and leads to the rupturing of the second fault. So these are very much what I prepared for today, and I will summarize it a bit. The first thing is that we discussed nonlinear models that can describe nonlinearities from source, path to site, and we develop numerical schemes that can solve these nonlinear phenomena. And then we use the numerical tools to study the side effect in Kathmandu Basin for the Gorkha earthquakes. And then we show how the nonlinearities can influence the fault earthquake triggering. And that's very much of it. And I would like to acknowledge all the collaborators that have helped me, give me very useful instructions. And that's it. Thank you.